Okay, so let us maybe start. So welcome everybody to the summer session of the QFT and Geometry Seminar series. And we'll open this season with a talk by Justin Kaidi from the Simon Center, who will discuss obstructions to gap boundaries. So take it away.
Great. Okay, so I'd like to start by thanking the organizers for inviting me to contribute a talk to this great series. So today I'm going to be telling you about obstructions to gap boundaries. And this is work in progress together with these fantastic collaborators, Zohar Komargodsky, Kantaro Omori, Sahan Saif Nashri, and Shuheng Xiao. So I think that many of you might have seen Zohar's talk at Strings about the same topic almost exactly a week ago today to the hour. But today I'll have more time, so I'll be able to give some more details. And also, I will try to emphasize things that Zohar didn't emphasize as much so that it's not boring to people who had already seen that talk. Okay. Right. But okay, speaking of boring, I do have to give you the obligatory introductory slides. So let's begin with something that we all know. So we all know that there is a phenomenon in QFT, which is that some theories which are gapped in the bulk are necessarily required to host some gapless modes on the boundary. In fact, there's some sense in which one could say that this is sort of the generic situation. For example, you can take your favorite U1 level K Chern-Simons theory. So here I took K to be even because I'm only going to think about bosonic theories, but I'll say more about that in a minute. For now, just think of your favorite U1 level K Chern-Simons theory. This theory is definitely going to have gapless stuff on the boundary. And this is part of the physics behind, say, the quantum Hall effect. So here's just an image of the quantum Hall effect, and I can just refresh your memory here. The idea is you have some slab of silicon, say, you put some magnetic field through it, let's say out of the slide, and then all of the little electrons go around in cyclotron orbits, but the guys near the boundary end up bouncing and moving down in, say, one direction. Okay, so you have some chiral modes which are localized to the boundary. And of course, this is just like classical Hall effect, but we know in the modern understanding that you can actually understand this in here as some Chern-Simons theory, and at the boundary you could have, say, some chiral bosons. Okay. In fact, there's not just one possible choice of gapless boundary conditions for U1 level K. Of course, there's any number of them. I could always just stack with some extra consistent CFT. But suffice it to say that no matter how hard you look, you will never find boundary conditions which are gapped for this theory. And in the current case, the fact that you can't have gapped boundary conditions is explainable via anomalies. In particular, the chiral central charge for the theory is non-zero, and hence there's a perturbative gravitational anomaly on the boundary, which in order to saturate requires having some gapless edge. But as we will see, it's a sort of interesting fact that the presence of gapless edge modes cannot always be explained by anomalies. So you can't always trace it back to this sort of thing. Concretely, the question that we're going to ask is the following. When exactly does a bosonic 2+1D TQFT emit a gapped boundary? And this is basically equivalent to the question of when two TQFTs emit a gapped interface. Because I could say have a TQFT T1 and T2 which share a gapped interface, and if I were to just fold that, I would get some gap boundary for the tensor product. Okay, so this is our question, and we certainly are not the first ones to ask this question. There exist already many results in the literature. This is just a small sampling of that. So what exactly do we have to add on top of this vast literature? So today, I'm going to go ahead and tell you about three main things. The first thing I'm going to tell you about is I'm going to give you a geometric reinterpretation of some of the previous algebraic results that existed in the literature. So much of this literature is sort of more formal, more mathematical. A lot of algebraic techniques or things like category theory are used. So for example, these authors here are category theorists. And so one of our goals is going to be to just phrase this in a language which is slightly more palatable to the average physicist. Okay, and then after having done so, I'm going to move on and present to you some new necessary and sufficient conditions for an Abelian, here I focus on Abelian, TQFT to admit gap bound. Now I should emphasize the word new here. There actually already exist some necessary and sufficient conditions out in the literature already, for example, due to these authors. But one of the nice things about our conditions is that they're going to be very highly computable. And so they're going to, in practice, be much easier to work with than, say, some of the previous conditions. Okay, and then finally, having done so, if I have time, I will conclude by introducing an infinite class of new obstructions labeled by 3 manifolds. Here again, restricting to Abelian TQFT. And then I'll conclude. Okay, so this is the basic outline of things. Now, because Abelian TQFT is going to be such a central player in today's talk, I want to begin by just giving you a lightning introduction to Abelian TQFT. Okay, so what's an Abelian TQFT? Well, all such theories, all Abelian TQFTs, can be written as K-matrix theories. So it's basically some, U1 to the nth, some copies of U1 Chern-Simons theory, and the Chern-Simons level is some matrix here, which is the K matrix. So it's some symmetric matrix and has to be quantized. And if we want to consider just bosonic systems, like we will today, then the K matrix has to be even. So its diagonal entries are even. So this is the generic Abelian TQFT. And what does this theory really look like? So the things that I can measure in this theory is basically I put in heavy external probe particles, and then I can measure Aharonov-Bohm phases between those particles. Okay. So yes.
Why do you constrain to bosonic theories? Or why do you restrict to bosonic theories?
So a lot of the proofs that I'm going to offer you for many of our statements will rely on the bosonic assumption. Yeah. So yeah, it would be interesting to extend things to the fermionic case, but we haven't done so.
Thank
you. Great. Okay, any other questions? Okay, good. So, right, good. So, okay, so we have in these theories some anyons, which are just, let's say, some Wilson lines, which are labeled by a charge vector alpha. Okay. And so alpha just gives you the charge under all of the U1 factors. Now, not every alpha gives you a distinct anyon. So indeed, quantum mechanically, so remember, we're just measuring some Aharonov-Bohm phases. And it turns out that all of the phases for the guy labeled by alpha and the guy labeled by alpha shifted by any element in the image of K are the same. So physically, these anyons are indistinct. And so the full set of anyons is not just Z to the K, but rather it's Z to the K quotiented by the image of K. Okay, so this is a set of all of the anyons, and in a moment, we're going to endow it with a group structure. So it's actually a group, and this is the so-called one-form symmetry group of the Abelian TQFT. So to specify the Abelian TQFT, I have to specify the one-form symmetry group, but I also have to specify some extra data. So for example, I have to specify these Aharonov-Bohm phases that I was just mentioning. And this is basically captured by this braiding here. So if I braid an alpha and a beta anyon, I get a phase, which is the braiding phase. And I also have to specify some spins. So if I have a loop like this and I want to undo the loop, then I get some phase, which is theta. Now this spin data is not independent from the braiding data, and we'll come back to that in just a second. But for now, let me just go right to fusion. So I also have to, in general, tell you about fusion. In other words, when I put the alpha and the beta anion on top of each other, I get out some resulting anyons, which generically are not, simple. It could be some sum of anyons with some degeneracies here. But a nice feature of Abelian TQFT, which is basically a definition of Abelian TQFT, is that there's a unique fusion channel. Okay, so these things here are just a delta function. So maybe just to give you a picture, if I put alpha and beta on top of each other, I just get out a unique anion, let's say alpha beta. Okay, and this means that I have the structure of a group under fusion. Okay, so in particular, all of the lines are, say, invertible. And so this is that group structure on G that I was mentioning a second. All right, good. So I mentioned this previously, but B and the spins theta are not independent. They're in fact related in this way. And so said in fancy language, the spins provide a quadratic refinement of the braiding. And so the upshot is that Abelian TQFTs can be completely specified by G, the one-form symmetry group, and the spins theta. Okay. So this is the defining data of Abelian TQFT. And now I can go ahead and reorganize this data slightly into something which is not quite equivalent. It captures slightly less information, but nevertheless, something which will be useful. And these are namely the S and T matrices. So I define matrices S and T as follows. I'll define T to be a diagonal matrix, where on the diagonal, I just have these spins. Okay. So this is extremely simple. And then I'm going to define the S matrix, and the S matrix is defined as shown. So I have this ratio of the spins, and then I divide by the order of the one-form symmetry group. Now, pictorially, I can encode the data in S here in this picture. So what this tells me to do is it instructs me to compute the amplitude of the Hopf link between the A and the B. And it turns out that this just evaluates this.
Justin,
right.
the B was defined as theta A plus B, and this is theta A times B bar? That's...
oh, right, you're asking, can I just do this in terms of, so you can just write this as B alpha beta over the square root of G if you want.
Thank you.
Yeah, so that's an alternative. You could have done that. Mm-hmm. Okay, good. Great. Okay, so we've defined S and T in this way, and the point of defining these things is that they actually have properties which are almost identical to the 2D S and T matrices. There's a slight normalization issue with the T here, but this S and T matrix here forms the so-called modular data. Okay, great. And I should say that S and T, of course, can be formed for both abelian and non-abelian theories alike. So we'll refer to the modular data of both abelian and non-abelian TQFTs and what follows. Of course, in the non-abelian case, you have to slightly update this formula. Okay, great. Okay, so I've just told you about the sort of ingredients in Abelian TQFT. And I would now like to return to the question of gapped boundaries. So when does an Abelian TQFT admit a gapped boundary? And actually, this question has already been solved. And I'm now going to quote the known result. Okay, so these authors say, Kristen and Salina, and in these papers as well, they obtained a complete characterization of gap boundaries, which is summarized in the following theorem. So an abelian TQFT, G comma theta, has a gapped boundary if and only if there exists a so-called Lagrangian subgroup of lines L in G. Okay, so this is some subgroup of the one-form symmetry group. And what we mean by Lagrangian is the following. So it satisfies two properties. First, this subgroup has to have all trivial spins. Okay, So for all alpha, all lines in the Lagrangian subgroup, the spins are equal to 1. They're bosonic lines. And the second condition is on the size of the Lagrangian subgroup. So the size of the Lagrangian subgroup has to be the square root of the total number of anions in the tube. So these two conditions define the Lagrangian subgroup. All right. So physically, what a Lagrangian subgroup is the following. You can think of it as a maximal non-anomalous one-form symmetry. Okay. So, right, this is the full one-form symmetry group. This is a subgroup of that. The first condition here tells you that this is a non-anomalous subgroup. Okay, basically because if the twists are trivial, the braiding is trivial, then it turns out you can proliferate a mesh of these things, as we'll see in a moment, in some unambiguous manner. And so this is where the non-anomalous comes from. And the maximal part comes from this condition on the size. Okay. So we're going to talk more about this in just a moment. But yeah, it turns out that if we gauge this Lagrangian subgroup, the theory becomes trivial. And we're again going to discuss this in more detail in a moment. So just hang on.
Can you comment how this was proven? Or was it proven or just based on examples?
No, so this is actually proven in these papers by Kapustin and Salina, and I'm actually going to offer you a proof right now.
Okay.
Yeah, so it's an alternative proof to their proof, which was more algebraic. But yeah, I'll give you the intuitive proof of why this is true in a second. Great. Okay, good. So yeah, but before giving you the proof, let me just give you an example, just so we sort of get a feel for how it works. So the example is going to be the following. It's just a product of two of these U1 level K trisomes. So U1 level 2n1 times U1 level minus 2n2. Okay. Remember that a single copy of U1 level K has non-zero chiral central charge. I said this on the first slide. So of course that theory does not admit a gap bound. But if I take the product of two of them, then the chiral central charges can cancel out if the levels have opposite sign like this. And so this theory might have a gapped boundary. So now to tell if it really does, I turn to this theorem. And I try to find a Lagrangian subgroup. And the first step of doing that is just to identify the one-form symmetry group. So in this case, we all know very well, I think, that the one-form symmetry group is just Z2n1 times Z2n2. And so in particular, the order of the one-form symmetry group is clearly 4n1 and 2. Now, the Lagrangian subgroup, if it exists, must have an order which is the square root of this thing. So in particular, the order has to be 2 square root of n1 and 2. And of course, since this thing has to be an integer, that means that n1 and 2 would have to be a perfect square. So if it's not a perfect square, then definitely there is no gap boundary. So as an example, you can consider U1 level 2, U1 level minus 4, say. In this case, n1 times n2 is 2. And since that's not a perfect square, this theory does not admit a gap boundary. But on the other hand, if you look at U1 level 2 times U1 level minus 8, in this case, n1 times n2 is 4. So it is a perfect square. And then you can actually try to construct the Lagrangian subgroup, and it turns out you can. So this theory will, at the end of the day, prove to have a gapped boundary.
What is the relevance of the minus sign in this example?
The relevance of the minus sign, this one? This minus sign is so that the chiral central charge is -1. And so then when I have the +1 and the -1 here, they cancel out, and I get chiral central charge 0.
Okay, thank you.
Okay, great. Okay, so this is Lagrangian subgroups. So we're now going to try and prove this in a nice geometric way. At least we'll prove half of this. Okay. Good. So I now want to give you a geometric interpretation of the Lagrangian subgroup, and then we'll prove, well, really just half of this theorem. using geometric means. Okay, and I want to emphasize something, which is that actually what I'm about to say on the next few slides is applicable to both abelian and non-abelian theories. So we're now going to let ourselves go beyond abelian for the next couple of slides. All right, so the idea is as follows. Let's
Justin,
say, yeah.
When you say non-abelian, you had three conditions that defines your abelian. Which one of them are you loosening, or does it matter?
Well, technically they're all slightly changed, but this one is also slightly changed, but the main one that we're loosening is just this one. So
Okay.
yeah, the point is that now I can have additional stuff here.
And also phases, presumably.
Phases as in non-trivial F symbols, you mean?
Yes.
Yeah, exactly.
Thank you.
Great. Yeah, so non-abelian ones are the guys which don't necessarily have like a group structure on the set of ends, because yeah, there's not a unique fusion chain. Okay, great. Any other questions before I do this geometric thing? Okay, great. So all right, let's say that our theory does have a gap boundary. If our theory has a gap boundary, then we can just go ahead and hollow out a tube, an empty tube, and put the gap boundary condition on the empty tube. Now, because the tube has gap or topological boundary conditions on it, I can shrink the tube and expand the tube however I want, and nothing's going to change. So in particular, I can shrink it down to a line, and then it should define an anion in the theory. And I'm going to call that anion fancy A. So this fancy A is not necessarily simple. It's going to be a sum over the anions little a here of the theory. And I'm going to have some, generically coefficients here, which I denote by Z0. So by emptying out the tube and then shrinking it, I define fancy A. Now fancy A is actually a very nice anion, because it has various nice properties, including the following. So first of all, it's pretty clear that the fusion and braiding of the fancy A anion are trivial. This is just pictorial, really. So if I start with this configuration of fancy A, then when I replace it with tubes, I get this, say, three-legged pair of cats. And then this is clearly, I can shrink it to get this configuration. It's obviously the same. And likewise, for braiding, it's just an empty tube. So these are clearly the same. Likewise, twisting the empty tube doesn't do anything. So the spins of the fancy A anion are trivial. And this in turn means that the spins of all of the guys which appear in the sum of fancy A are also trivial. Okay, so the spins are trivial for any A which appeared in that sum. Another way of writing this condition here is just that Tz is equal to Z. Remember, the T matrix was just a diagonal matrix with the spins on the diagonal. So clearly, for any non-zero Z, since theta is 1, this is true. But something which is less, or I should say more non-trivial than Tz is equal to Z, is that actually Sz is also equal to Z, where S was the S matrix. And we can prove that graphically as follows. So first, remember that S was obtained by looking at the amplitude for the Hopf link between A and B. This gave me the AB element of S. Now the picture to consider is the following. Let's consider the Hopf link between fancy A and little a here. So I'm just redrawing it here. Now we can use the definition of fancy A to expand this as a sum over these Hopf links between B and A. And then we just use the definition of S. So this is like this. Now, there's some overall factor that I'm going to ignore because it cancels out. So the upshot is that this picture here computes for you S times Z. On the other hand, I can go ahead and take fancy A and replace it with the empty tube. And if I do so, then this configuration topologically is just a solid torus with the gap boundary conditions on the boundary. And then the A anion runs around the longitude. Okay. So if I compute the partition function of this thing, that computes for me the dimension of the Hilbert space on D2. But in particular, it's D2 punctured by the A anion, right? It's just like a cross section of this solid torus. And it turns out that this thing here, I won't prove it now, but if you want the proof, I can give it later. It turns out that this thing here is Z0. So this gives me the Z. And so this picture proves S is equal to Z. All right, so we have a fancy A anion. It has trivial braiding and fusion, and it also satisfies TZ is equal to Z and SZ is equal to Z.
Justin?
Yeah.
I'm confused on how things are acting and what is acting on what. The T and the S matrices, are they a representation of something that I should see?
So S and T can be thought of as giving you a projective representation of PSL2Z.
Yeah, but is that part of some other group that's acting or something else? Or is it the whole story, or is there something missing?
I'm not sure I understand the question. I don't quite understand the question. Sorry.
Okay. Because earlier.
Are you asking whether there are other generators?
Yes, for example.
Other generators of what? Sorry.
Of whatever is this. So is this PSL? So TNS, I should say, they're representation of PSL2Z.
Yeah.
But does this fit in some larger group that's acting on these lines? Maybe not even a group, some algebra that's acting on these lines. So how am I picking things out? Does it always exist, for example?
No, I don't think there's any. I mean, I think the easy way to think about this is as follows. You could think of this thing as, say, a gluing matrix. So maybe it's best to just think about this in 2D, where we're really familiar with S and T. So I mean, in the 2D case, you can think of Z, let's say AB. Here I'm just considering Z with one component being 0 always, but in any case, I could consider ZAB, and this is just a modular gluing matrix. So
yeah.
The partition function would be something like this. And the S and T then that I'm talking about here are almost literally the same exact S and T that act on chi A and chi B in the usual way. These things form a vector valued modular function with the specific representation just being that generated by this matrix representation of S and T. I don't think there's any more structure beyond the PSL2Z.
But the modular group could be larger.
Can it? I'm not sure. I mean, maybe does one of my collaborators have something more intelligent to say? I'd be happy to talk about it in more detail after.
Maybe we
sure.
can postpone it later and you
Yeah, we can talk
continue.
later.
Yeah, I don't know if, no, I don't think that there's anything more, but yeah, we should talk about it after.
Okay, maybe what I have in mind is a little different. Okay. I can ask you more precisely later.
Okay, great. Thank you. Yeah, thanks for the question. Are there any other questions? Okay, good. Right. Cool. So, okay, we were talking about the fancy A anion. It had trivial braiding and fusion. TZ was equal to Z and SC was equal to Z. Okay, that's the status so far. And I actually wanted to prove one more fact about the fancy A anion. So this other fact just comes from the equation SZ is equal to Z that we saw before. This is it in component form. And if I take the A is equal to 0 component of this, I end up getting an equation for the dimension of the A anion in terms of the quantum dimensions of the other anions in the theory. If you're not familiar with the quantum dimension, it's defined here, but we actually don't have to worry about it because we're about to go back to abelian TQFTs. And abelian TQFTs have all of the quantum dimensions being 1. So if we now retreat back to abelian TQFT, then this formula is simply that the dimension of the fancy A anion is the square root of the order of G. And at this point, this number here should be sort of familiar. We recall something else which had size, which was square root of the order of G. And that something else was this Lagrangian subgroup. Remember, there was some Lagrangian subgroup which had size, which was the square root of the order of G. So in fact, this suggests a relationship between the fancy A anion and the Lagrangian subgroup. Indeed, there is such a relationship. So it turns out that the fancy A anion for abelian TQFTs can be thought of as a sum over all of the anions in the Lagrangian subgroup, just like this. And they have coefficient 1. All right, so it's just a sum over all of the lines in the group. That's all there is to it. But what we've seen is that A actually also exists in non-abelian theories. So it goes beyond just non-abelian subgroups, or sorry, Lagrangian subgroups. But yeah, so in reference to this fact, partially in reference to this fact that they're related to Lagrangian subgroups, we'll call them Lagrangian algebra anions. Okay, and of course these Lagrangian algebra anions have been developed in the math literature and used in the physics literature, etc. But okay, so what we just proved geometrically is that every TQFT with a gap boundary has a Lagrangian algebra anion. And I'm now going to show you something which is pretty interesting, which is that we can obtain the trivial TQFT by gauging this Lagrangian algebra anion. Okay, so first I have to tell you what I mean by gauging a Lagrangian algebra anion. So what I mean by gauging a Lagrangian algebra anion is I mean inserting a fine mesh. Okay, and by fine mesh, I really mean something dual to the triangulation. Okay, so the idea is as follows. I start with my 3 manifold here, this black circle, say, and I triangulate it. So that's these blue triangles. We should think of them as tetrahedron. And then I go to the dual triangulation, which is this red lattice, and I put the Lagrangian algebra anion on that. Okay. And it's actually pretty much, it's unambiguous how I do this. If I change the triangulation, nothing changes because these things had trivial fusion and braiding. So I can unambiguously put in this mesh. And now let's show that this gauged theory with the mesh is the trivial theory. So the way we see it is easy. We just replace the mesh with the empty tubes. And so here I've excised this interior piece, which is really just some handle body. So I've removed some handle body, and what is left over is actually another handle body. Okay, so by removing or by replacing this by the empty tubes, I just get a handle body. This splitting into 2 handle bodies, by the way, is referred to as a Heegard splitting in math literature. So in any case, I see that the gauged theory, its partition function is just the partition function of this handle body. And in fact, this can always be decomposed into a product of disk partition functions. So no matter what manifold I started out with, once I gauge the algebra anion, I just get some product of D3 partition functions, which I can normalize, say, to 1. So I just get the same result on any manifold. And so this is the sense in which gauging A gives me trivial. Okay. Yeah, and then actually, yeah, once you know this fact, you can show that if I, gauge only part of, if I gauge A only in part of the space, and I put some Dirichlet boundary conditions on the interface between the two parts, this will actually define a boundary condition for us. But I won't go into more detail on that. All right. So let me say one more thing about this Lagrangian algebras, specifying now to the
Sorry, hello, can I ask you a question?
Yes.
With respect to Kapustin-Saulina.
Yes.
So if I remember correctly, they also define a line called curly A. However, the reconstruction is slightly different. So they also have some sort of surface operator, topological surface operator, but instead of constructing a tube, so using it as a gap boundary, they take a strip of it. And then they prove, so and they say when the strip is very thin, it behaves like a line. They call this line curly A, and then they prove various properties like give you some associative algebra and so on.
Right.
So is their A the same as yours, or is it something?
I would, if I recall correctly, I would say that RA is a special case of their A. So their A, I believe, is just a generic so-called like Frobenius algebra element. It satisfies various properties such as, you know, it has some multiplication, some co-multiplication, etc. But it's missing something. Well, yeah, it's missing, I guess, a couple of things, but I don't think that there's any statement, for example, on the size of this algebra element. Whereas one of the crucial properties of the Lagrangian algebra element is that the order of it is the square root of the total quantum dimension of the theory. That's an additional input. So their A's you could also gauge, but it won't give you a trivial theory. Whereas this is a special anion, which once I gauge it, I get rid of all of the other anions.
Thank you.
Mm-hmm. Any other questions? Okay.
How do you see that you get rid of all the other anions, that you cannot introduce other anions?
Well, there's probably numerous ways to do this, but so there's some three-step gauging procedure that one can generically do. So like step one is, let's say I want to gauge some subgroup. So step one of the gauging procedure is I identify everything which is related by fusion with, you know, one of these guys. And then the second procedure is I get rid of non-invariant stuff. And then there's a third step. I don't quite remember. But in any case, if you just do these three steps, you can see explicitly that no anions are left over.
Thank you.
Okay, good question. All right. Good. So let's now focus on the Abelian case momentarily. Actually, I think the rest of this talk will be Abelian, but just for this slide especially, Abelian. So in the Abelian case, I told you that the Lagrangian algebra anion A was interpretable as just a sum over all of the elements of the Lagrangian subgroup L. And in this case, it's easy to see that the formal gauging of A, which was the putting in the fine mesh, is equivalent to our usual notion of gauging, as in summing over some, in this case, discrete gauge fields. And the way that we can see this is just very schematically as shown here. So let's say that I have my three manifold, which is not actually a torus, but you know, we can use our imagination here. So let's say that this was our three manifold. I would put the fine mesh. So in particular, I would have one of these fancy A anions on all of the one cycles. And then I just use this to replace this by a sum over all of the elements of L inserted along all the cycles. And this is just like our usual notion of gauging L. Okay. So you remember that in 3D, if we gauge a one form symmetry L, we're going to get back a dual zero form symmetry, L hat. And conversely, if we were to gauge L hat, we'd go back to the original. Now, I just argued for you that when I gauge L, I get a trivial theory. So that means that if my theory has a gapped boundary, then I can gauge L to get a trivial theory. But that also conversely means I can start with the trivial theory and gauge L hat to get the theory I started with. In other words, any theory which has a gapped boundary is an L hat gauge theory. In other words, it's a digraph-Witten theory. It's some discrete gauge theory. I start with the trivial theory, I just gauge some zero forms. Okay, so this is a nice sort of non-trivial result. All right, so thus far I've told you a lot of things about Lagrangian subgroups and Lagrangian algebra anyons. But actually, if you're just given a TQFT, actually finding a Lagrangian algebra anion is not really straightforward. Okay, this is partially because in general it requires knowledge of, say, F matrices, et cetera, et cetera. So I'm now going to give you an alternative set of necessary and sufficient conditions for the existence of a gap boundary. And here I'm going to focus on Abelian TQFTs only. And these new necessary and sufficient conditions will have the virtue of being very highly computable. Okay, the only data I'll need to input is just the spins, and there's just some very simple operation that I'll do on the spins to extract whether or not there's a gap boundary. So in order to give you these new obstructions, I now want to first give you a reminder. So a reminder, remember that the chiral central charge, C minus, was the simplest obstruction to having a gap boundary condition. This we already mentioned. And something which is really nice is that the chiral central charge can be written in terms of the defining data of the Abelian TQFT, that is to say G and theta, as follows. Okay, so it's a really simple expression. I just sum up all of the spins, theta, for every anion that I have in the theory. Okay, and then I take the phase of that sum. And that gives me the chiral central charge, at least mod 8. So this is a really nice formula. And now we're going to go ahead and generalize this formula. So we're going to take this formula and we're just going to replace theta with theta to the nth power. And we're going to denote this quantity by Cn, and we're going to refer to it as the higher central charges, following these math papers. Now, it's not clear why this quantity would be interesting or physically relevant or provide any sort of obstructions, right? All we've done is just arbitrarily added an n in here. But it turns out that these quantities actually do provide obstructions towards having a gap boundary. And this is summarized in this theorem of, I think, really the second math paper here, which says the following. An abelian TQFT G comma theta has a gapped boundary only if these higher central charges are trivial for all n such that this GCD condition is satisfied, namely for all n which are co-prime to the order of the one-form symmetry group. Okay, so once more, an abelian TQFT has a gap boundary if and only if the higher central charges are trivial for n co-prime to G. This gives me necessary conditions for the existence of a gap boundary. Okay, it's necessary that these be true. However, you can also get sufficient conditions from these higher central charges, and this is one of our main results. So the statement in our paper is that if we extend n and allow it to violate this condition, but satisfy a broader condition, we can get necessary and sufficient conditions. So let me read the theory. An abelian TQFT has a gap boundary if and only if the higher central charges are trivial for all n satisfying this broad condition. So I'd now like to give you an example of this in practice. Okay. So let's illustrate this by means of an example. And here I'm going to use a simple example that we already analyzed before. So we already know the answer in this case, but it's a good check of this. Okay, so I want to check if U1 level 2 times U1 level minus 4 has a gap boundary. And in order to do so, I have to compute all of these higher central charges here for n which satisfies this. So the first step is we identify the spins, because at some point I have to sum over the spins. So U1 level 2 turns out to have this set of spins. U1 level -4 has this set of spins here. And if we put them together, we get this set of 8 spins here. The exact values are not important. Just suffice it to say that it's actually really easy to calculate this. So in any case, in total, there's 8 anyons with these spins. And so the order of G is 8. And now to ask the question about gapped boundaries, I first find all of the n which satisfy this condition. Okay, so in this case, the order of G was 8. So I search for all n satisfying this guy here. And it turns out that the results are just 1, 3, 5, and 7. Now, of course, there could be an infinite number of things which are co-prime to this. But the point is that n is actually mod 8 periodic, because the spins are at max just 8th roots of unity. And remember, n is just the power of theta. So actually, there's only 4 higher central charges we have to compute. And we can now compute them. I just literally sum these things up. So you can just do it by hand, and you'll find that Xc1 and Xc7 are 1, but Xc3 and Xc5 are -1. And since they're not all trivial, there's no gapped boundary. But on the other hand, you could go ahead and do the same exercise for U1 level 2 times U1 level -8, and you'll find that this guy does admit a gap boundary.
Justin?
And yeah.
Do other values of n have any meaning if you compute psi n for other values of n which don't satisfy this GCD condition? Is there any pattern?
So they might have some meaning for some things, but for the current problem of interest, no. There can be some other values of n which, for example, the theory can have a gap boundary, and yet, yeah, the main problem is that when n is not satisfying, like for general n's, it can occasionally be the case that these sums are just 0. And so then, there's no real notion of these higher central charges in the first place.
I see.
Yeah, so to the best of my knowledge, no, there's not really any significance to those cases.
Okay, so Juven raised a hand, so if you can ask the question.
Yes, thanks. So this particular example can also be solved from Lagrangian subgroup type of condition you mentioned.
Yeah.
So, but I think, am I understanding correctly that you rephrased the Lagrangian subgroup condition by defining a quantity called this Kaidi, and then change that condition such that I mean, this particular example basically can also solve from the subgroup. So what you did is basically a rephrase of that condition to the quantity you define. But perhaps in some way that the quantity you define can be more general, which I haven't seen the impacts on that. But
no, it can.
And so then the notion of higher central charge you introduce seems partially actually is captured by the Lagrangian subgroup type of condition, right?
No, it's 100%. I mean, the Lagrangian subgroup. So here I'm just talking about Abelian Tqft. And in the Abelian Tqft, we already know that the Lagrangian subgroups are necessary and sufficient. So no matter what I do, I can't improve that. This is just an alternative condition.
But then you try to define a quantity called Kaidi that you call higher central charge, right?
That's correct. And the new condition is in terms of that Xc, which was actually not defined by us, really. It's defined by these people. But yeah, this theorem is due to us. Mm-hmm. Yeah, the point is just that, so for example, here I was doing really simple examples, but if I give you this, if I tell you to find me the Lagrangian subgroup for spin 8 level 1 times SU3 level -1 squared, so tell me if a Lagrangian subgroup exists for this theory or not, or something like, G2 level 1 to the 20th power. In practice, you're going to have a hard time finding or not finding the Lagrangian subgroup, but you're not going to have a hard, so let me ignore this case because it's not abelian really, but this is abelian. So you're going to have a really easy time just checking what the x's are for this, but you're not going to have a fun time checking if this has a Lagrangian subgroup. So yeah, it's just an alternative. And really, I wouldn't even say that conceptually it brings anything to the table, but really practically, computationally, it's an improvement.
Mm-hmm. But somehow you call the name higher central charge. So is there also some physical understanding for that? You'll say. I can. So if you want a physical understanding, I assume you want, like, say, some 2D interpretation. And if you wanted it as like a piece of a correlation function or something like that, unfortunately, no. And there's not really, even to the best of our knowledge, some connection to an anomaly. So again, no. But there is some sense in which there's a physical meaning of these. It's a sort of abstract one, but I can tell you it if you want. And that's the following. So the S and the T matrices, it's sort of a remarkable fact, take values in some cyclotomic extension of the rationals. I'm going to write it like this. The fact that T does this is obvious, but the fact that S does is not obvious. So in any case, because the modular data takes values in some cyclotomic extension, I can discuss the Galois group associated with this extension. Oops, Q, C, Q. And I can now consider an element in the Galois group. So what these elements do is they leave the rationals unchanged. And let's say the nth Galois transformation takes C to Xn. So in particular, the Galois transformation acts on the spins of the Tqft and takes them to the nth power. So given any Tqft, I can actually have a full Galois orbit of Tqft's, which are obtained by starting with the original theory and then transforming via Galois transformation. And from this result here, we see that the higher central charges are just the usual chiral central charges for the Galois conjugate. So what we're saying, in a sense, is that for a theory to have a gap boundary, it does not suffice for that theory's central charge to vanish. You actually have to check all of the elements, or at least the ones satisfying this, the elements in the Galois orbit, and you have to check that those theories' central charges also vanish. This might not be very satisfying physically, but it's one interpretation. Yeah, thanks. So I have a comment again, but I will let you go after I leave this comment. I think it's related to Zoha's talk. So I do have a maybe physical way to say this, maybe more physical than what you say, both from the bulk and boundary. I think the boundary way will just be what Zohar probably already said, is condensation for anyons. They are compatible. So there are some mutual commuting conditions, like a braiding in order to condense that set of anyons. That's the kind of conditions you have from the Lagrangian subgroup side, but that's from the boundary side. But on the bulk side, because you are generalizing the chiral central charge, the chiral central charge is captured by perturbative local gravitational anomaly, which is also invertible anomaly that captured by invertible Tqft. But that the Lagrangian subgroup condition is more like saying the non-invertible type of anomaly, which usually not called anomaly. And one's type of thinking, Xiaogang thinking, will call this a gravitational anomaly, but which confused the community because it's usually not called anomaly.
You just mean a relative.
Yeah. Okay, so I think for some people you can still call non-invertible and also global type of gravitational, but non-invertible anomaly, and that's the kind of condition you try to phrase, I suppose. Except that you define this quantity somehow still a phase, a c, right? Because the absolute value is still 1.
Yeah.
Which somehow still kind of not sure why still captured in some invertible way. But I suppose it's not invertible anomaly for sure. So I don't think can capture by invertible Tqft is non-invertible type of. Yeah, that's all I can say.
Mm-hmm. Yeah, I would. I think we should talk about it.
Yeah,
more.
thanks.
Yeah, I'd be interested. Mm-hmm. Okay, so I noticed that I have 5 minutes. So, but I'm almost done. So perfect. Is there any other quick question? Okay, so I just want to give you one brief geometric interpretation of the higher central charges that we just introduced. Well, yeah, I don't know if this is more physical than the Galois thing I said. I think probably not. But in any case, this is how you could encounter a higher central charge out in the wild. And so, yeah, so recall that the chiral central charge is the phase of the S3 partition function. And in exact analogy to that, it turns out that the higher central charges are phases of lens spaces. So if we wanted to phrase things in terms of the Galois stuff that I just said, which maybe we don't, but let me just say that the statement would be that the S3 partition functions of Galois conjugate theories are just the same as the lens space partition functions of the originals. But we're not going to use that, so don't worry. So anyways, what we've seen thus far is basically that the chiral central charges capture the phase of the S3 partition function. The higher central charges I quoted for you are the phases of lens space partition functions. And in fact, there's a slightly more general result, which is the following. It turns out that an abelian Tqft has a gap boundary only if the phases for all three manifold partition functions are trivial, as long as that three manifold satisfies this condition here. So the first homology group of that three manifold is co-prime to G. Okay, note that this condition here is a direct analog of this condition that we saw here, right? Because I told you that for the higher central charges, M is the lens space. And of course, we know that this guy here is Zn, and the order of it is N. So we reproduce the previous thing. All right, so here we see that we now have some infinite number of obstructions, which are given by the phases of partition functions of three manifold satisfiers. Of course, this is sort of a moot point because we already obtained necessary and sufficient conditions. So this is just beating a beating a dead horse, but okay, in any case, this is a theorem that can be proved and we prove it.
What about if there is not just torsion order, but you have some free part to H1, like a 3 torus?
That's a good question. Yeah, to first order, I would just write that off as not satisfying this GCD condition and not considering it, but one could potentially salvage it. Yeah, in fact, right, at various stages of this project, there was some discussion of salvaging this. Yeah, let me not comment on it because I don't actually have anything intelligent to say. Sorry.
Okay.
Okay, great. So I have 2 minutes left, and actually 2 minutes is enough for this proof. So let me actually just give the proof. It's extremely simple proof, and it goes as follows. So so remember, let me just read the statement one more time. An abelian Tqft has a gap boundary only if the phase of the partition function is trivial for every three manifold satisfying this. So proof. An abelian Tqft, we already saw, has a gap boundary if and only if there exists a Lagrangian subgroup L. And remember that the Lagrangian subgroup L had the property that if I gauge it, I get the trivial theory. So in particular, if I take my original partition function, couple it to a background gauge field for L, and then do the gauging, so I sum over A, then I should get the partition function of the trivial theory, so just one up to some normalization factor. But remember that we're working on manifolds where this GCD condition is satisfied. Okay, this GCD condition, it turns out, implies this GCD condition here, where I replace G with L. This is simply because, remember, L squared was G by definition. So this is obvious. And it's actually also a simple step to show that this thing here implies that the first homology group of M with L coefficients is trivial. And then the Poincare dual statement is also true. So the second cohomology group with coefficients in L is, there's a little bit of math fancy footwork that went into here, but the upshot is that this thing here means that H2ML is trivial. And hence there's actually no gauge fields here to sum over. So actually this sum here just collapses to the original partition function. And so we conclude that the original partition function is just 1 over this stuff here, which ends up being L, but it's not important. The only important thing is that it's positive. That's the proof. So that's all there is to it. Okay, great. So that's basically all I wanted to tell you. Let me go ahead and conclude. So what have we done in this talk? Well, first of all, we gave a geometric reinterpretation of various algebraic properties of Lagrangian algebras. Okay, and here things were applicable to both the Abelian and non-Abelian cases alike. And then in the second part of the talk, we went on and we discussed some new necessary and sufficient conditions. They don't give us any more or any less than the Lagrangian subgroup condition. But in any case, we found new necessary and sufficient conditions for Abelian TQFT. And the virtue of these things was that they were highly computable. Okay, and much easier than looking for this Lagrangian subgroup. And then finally, I briefly mentioned an infinite number of obstructions for Abelian TQFTs, which were labeled by 3 manifolds. And I didn't really tell you this, but these things are, again, very easily computable. You can just compute them via S and T matrices using the surgery presentation of the partition function. Of course, the remaining main open question that I would leave you with is, it would be great if we could generalize 2 and 3 to the non-Abelian case. So it's not clear to us yet how to do so. Okay, so thank you very much.
Thank you, Justin, for the beautiful and very clear talk. So let's thank Justin. So are there any questions? Okay, so let me maybe start. So this science that you define, and you used n to be an integer. Is there any, can it be useful to analytically continue n in n to some complex number? Is there anything to be extracted from such a thing?
Not that I'm aware of. That would have, yeah, I guess even less. I would be even less sure of the physical
of course.
of those than of even the ones with the integer, which I'm not sure. So yeah, I can't say anything useful about that. I'm not sure.
So, okay.
Let's see if there's something going on in the chat.
Yes, so Juven says it will be nice to have necessary and sufficient conditions for non-Abelian TQFT.
Right. I agree with Juven. There exist them. So as Shuhang just said, one of them is the existence of the Lagrangian algebra object, to be contrasted with the Lagrangian subgroup, which was just for Abelian. There's also a statement, which I believe is general, which is this free Telemann result that a theory has a gap boundary if and only if it's Tarai of 0. You know, I think what one would really like is something which is like the higher central charges, which is very easy to compute. Yeah. So Juven says we have
a necessary, sorry.
Yeah, I think Juven has necessary conditions. Indeed, in this paper with Lon and Wen, that I think he quoted above. Yeah, so you guys have necessary conditions. Yeah, it would be great to have sufficient conditions that are of the same level of like simplicity. Like you can express them in terms of the modular data, etc. Yeah, I agree with you.
Do you have any more general? Yes, Sakura, please go ahead.
Go ahead.
You are muted, Sakura.
No, I said, go ahead, go ahead.
Wow. Sorry. Do you gain any more general insight into like general RG flows, like when the Tqft anomalies vanish? Do you actually have a gapped theory in the infrared or not? Does it help you with such questions?
Yeah, you mean some notion of anomaly matching, but for higher central charges. I do not think that these things will give you RG invariance. So I think that the answer is likely no. Yeah. I think the answer is likely no. Yeah. I think not.
I think there could be RG invariance from the 2D point of view, but not 3D.
From the 2D point of view.
But can you imagine that there is something like that will be like in general dimension that we're missing some extra conditions like to Tqft anomaly matching? Or you think it's very special to this setup, to 3D with 2D boundaries?
Yeah, I mean, I would not even know if there's a notion of chiral central charges for higher D. I feel like their definition required a lot of special stuff about 2+1D. But yeah, I don't know. I don't know if. Yeah.
Sakura, you had a question?
Yeah, it was actually related to something you asked at the very beginning, but I actually forgot what you said in answer to Shlomo's question about fermionic. The fermion, so you focused on bosonic cases, but there should probably be a similar thing you could do for fermionic. So what was your answer there? And maybe you can elaborate.
Well, my answer, I think, was to just sort of avoid the question. But so one of the main things is that here, we just used MTSP data to construct these invariants. Of course, one could imagine doing the same exact thing for the fermionic case, but then you have to deal with, like super MTCs. And it's certainly doable, but we just didn't want to, I think, deal with it at this stage. In the math literature, this question has been studied also for the super MTCs. So I think one could do what we're doing in that case as well, but we haven't done.
Mm-hmm. Okay.
Are there any additional questions, Justin? Okay, if there are no more questions, let's thank Justin again. And maybe we can switch off the recording.